ladies and gentlemen, dear Chairman, first of all, I would like to thank you very much to invite me to give this lecture on basic physical concepts and instrumentation in PEDMR. I'm very honored to be here in Kuwait. It's the third time I'm here, and with each time I'm here, it's much more pleasure to be here and to come back. And so the subject of this talk, as already mentioned, is instrumentation in PEDMR, and I'd like, first of all, to remind that I'm giving this talk from a physician's point of view. So I hope all the physicists who are in the audience are not too disappointed that I'm not showing too much formulas, but I'm looking at it from a historical and a practical point of view in order to give the introduction for the talks on PEDMR, which will follow. So everybody of us knows the success story of PET-CT, where the first publication and the first prototype was thought in 1994, funnily by the Geneva team at that time. And 4 years later, in the US, the first prototype was produced with a fully integrated PET-CT system, and which went a big success, and now in most regions, nuclear medicine department without PET-CT is almost unimaginable. So let's look how it went in PEDMR. It was a little bit different, and when we look at the timeline, the development also began rather early in the 1997, with, let's say, similar development of technology in small animals, and also already in some clinical and preclinical applications. So how did it start? If it starts, yes, it works. So the first publication on it was in 1997 about the principle from physicists who developed an imaging system basing still on photomultipliers. And the problem in MR, everybody of us knows, photomultipliers in a magnetic fields don't work. So they had to find a possibility to get the light out of the magnetic field in order to have a good image quality. And what they did, that they used glass fibers, as we can see here on this example. This is a photomultiplier, which is on a normal, which was based on normal natrium iodine crystal, and then with fibers they went back to the to the computing unit in order to generate the images. Some years later, still in the small animal part, the first complete insert to a 7 Tesla MR was developed from more or less the same group from Tübingen, which had a 7 Tesla small animal MR, and they constructed an insert to image whole mouses in the system. And how did it work? This is the image of it. It's the ClinScan 7 Tesla. Here's the insert where you can put the mouse in, and that were the first comparative images between PET-CT on the upper row and PEDMR, where they had one mouse with a tumor which was FDG avid, and they produced the first images on that. So how did it work exactly? Here's you can see a view a little bit more exactly, the stable magnet around about it, then a very small detection unit for the PET, and then the fibers who were leading the image signal outside of the machine, and the mouse, and then the RF coil. So how did we get then from small animal PEDMR to human PEDMR? Well, the first human PEDMR was not an integrated system. It was still working with the insert on a regular 3 Tesla MR, which was also developed, or the whole system was also developed by the same group in Tübingen in Germany. And they developed a head insert for this whole body MR with a small, very small diameter. Here are the detecting tools into. And the first thing they scanned was still mouses, because it was not yet suitable to put a whole human being, that's clear, and even not for the first tries, they couldn't even put a brain into it. However, the first whole body mouse images they generated were quite acceptable. with really an inline inline and simultaneous PET MR acquisition. On the basis of this, prototypes, fully integrated PET MR systems were developed. So the next step was then, how do we come from small imaging to human imaging, to have gantries where you can put into a whole human being. And then there are three different approaches. I think everybody of us knows them. Either you have sequential PET MR, so a PET MR which is more or less close to the MR unit. You can do integrated MR with small detecting range of PET, and the future maybe with new detector technologies will be a PET detector which covers the whole tunnel, and thus you get a very good and very great field of view for PET and MR at the same time. The first commercial PET MR was put on the market by Siemens, which consists of a 3 Tesla MR, a full time-of-flight PET system, PET scanner, both of them in a distance of 3 meters, just in order to avoid any nuisance of the PET scanning by the MR magnetic field. And the first prototype of these machines was used at Mount Sinai in the US. And we in Geneva had the great luck to be the first in Europe to work with this machine. And in our hospital we had a little bit of a particular situation because there was no surface where we could put this machine. So everybody was happy, we have this machine, but where the hell will we put it? And the solution we choose there, we put it into a container. This is a normal design of a PET MR unit with a procedure room, the operator room, technical local, and other locals. And in Geneva we did it like that. Here are the plans. This is the rooms. These are the rooms which are still belonging to the hospital. And here you can see the scanner container, which is just put adjacent to the hospital, which for us had a big advantage. When the PET MR was constructed in the container outside of our hospital, and then it was delivered, ready to plug and play. We plugged it, we did all the calibration work, and we could start right away, very, very fast in doing PET MR procedures. Oops. So, getting back to the technical challenges, this technique is possible as subsequent scanners when you're working with conventional photomultipliers, and you can apply full time-of-flight technology. If you're doing integrated MR, you have to replace the conventional photomultipliers, which are, on one hand, they are big. So already a conventional MR gantry has a diameter of some 60 to 76 centimeters at a maximum. If you want to do in addition to the magnets of the MR, still PET detection systems, you get into big problems due to the size. And the other one is, this is the detection when you scan only PET, and this is the image quality when you scan PET and MR simultaneously. So there's big distortion to the magnet field from gradient coils. So what was done by one of the other vendors, together with the Tübingen group once again, they developed avalanche photodetectors, which are now onto its way to semiconductors, which are much smaller and which are not that sensible. They are still a little bit, but not that sensible than the conventional photomultipliers. What are the properties of these photomultipliers and APDs? So when looking at the size, they are much smaller, the gain is faster, rise time is a little bit slower, and they are not sensitive to MR. But on the other hand, with this technology, you can't do full PET MR. You can't do time-of-flight PET MR imaging. So here, how they are consisting, there are four 848 arrays of these LSO crystals in the basis, and then the avalanche photodetectors, which are very stable to the temperature. And this was then the first prototype which was developed, as I said, with a head insert. They put these detectors into a head insert and the fibers outside for the computing in order to have a minimum of nuisance. And that were the first images which were created. They had very good PET quality, with a resolution down to 1 millimeter in this phantom setting, and also very good MR quality. And this is now the idea how fully integrated PET-MR. Sorry about that. This is now the definitive design, how Siemens is delivering this machine with an integrated PET camera around the detectors, within the detectors and the gradient coil, out of the gradient coils, but within the stable magnets of the PET, of the MR system. Another approach was chosen by GE, and here I thank for these slides, which I got from Professor from Schultes from Zurich. There they have the approach that they are working with a a normal time-of-flight PET-CT in one room, and in another room 3 Tesla MR, and the table can be undocked from one and docked to the other machine, and so you can avoid movement artifacts, other artifacts, and you can do very good software fusion of these two separate modalities. The big advantage is you can really do full time-of-flight PET-CT with diagnostic CT. You can use CT for attenuation correction, and at the same time, without having to call once again the patient, you can perform right away the MR, and the next patient can already go to the PET-CT. So the use of the machines can be optimized. And on the other hand, the image quality between normal PET-CT, normal PET without time of flight and time of flight is somehow astonishing. So how about the surface coils? Because that's the problem. I will talk on that also a little bit later. What are the problems there? And therefore, the sequential systems use a glove approach, so the patient is slipped out or into the surface coil, set up without any displacement when entering the MR, which is the sequential systems. In all systems, the vendors had to redesign the coils with a minimum of metal in the field of view of PET in order to avoid attenuation artifacts by these metal parts in the coils. On one hand, and on the other hand, you have to keep these coils as small enough because there's attenuation also very low, but there's attenuation from plastic, and MR doesn't see the coils, so in order to avoid also those artifacts in attenuation correction when using MRI for attenuation correction. And finally, which is common in all systems, you can identify the location of the coil components using UTE or zero TE sequences. How does this work? Here, one example of an UTE sequence on a chest. So you can see here the MR of the chest, and by this here you can see the metal parts of the coils, and then when you can see them by the UTE, you can also correct for them. So in summary, all vendors at this time use state-of-the-art 3 Tesla MR scanners. The one from Philips has a sequential design in the same room, which allows for full-time flight PET acquisitions. Siemens Healthcare is at this time the only one which has a fully integrated PET MR, but without the possibility of doing time of flight. And finally, GE Healthcare at this time has a sequential design in 2 different rooms, which permit full time of flight PET-CT and MR, but finally there are 2 strictly distinct systems. So this for the technical part, and now let me just talk on some hot topics in clinical PET MR. One thing, and therefore it was one of the major reasons why we went also to PET MR, is decrease of radiation exposure, and then there will be also some talks on that tomorrow. Time consumption is a very important issue in terms of patient throughput. Attenuation correction, there is still much work to be done. And finally, what are the killer applications, the clinical applications for this machine? Now we have some experience with that. We have some ideas where we could go in this direction, and the next months and years will show if we are right with our predictions. And finally, what is the diagnostic accuracy compared to the standard methods, and certainly also costs. So just some words on radiation exposure. Everybody of us knows how much radiation is coming from PET. Depending on the activity injected, we are up to 5 or a little bit more millisievert. New detector materials permit now to decrease the injected averages up to 50%. From this is unchanged in the PET-MR system. From CT, also there are now low-dose protocols, and I think also Philip will talk a little bit about that tomorrow, this afternoon in cardiac imaging. When looking at low dose without contrast, you can go down to 2 millisievert. If you do full dose protocols, you have up to 10-20 millisievert. So there's still potential pretty much coming from CT, but there is a potential decrease, and as we know, there's no irradiation from MR. When looking at time consumption, this is, in my opinion, the biggest issue. PET-MR needs to become very fast in order to have significant patient throughput. So you have to have fast sequences on the one hand side, and you have to limit the number of MR sequences in order to have a diagnostic at a reasonable time. Here was one publication from Germany who worked out what one can do in whole body MR at 3 Tesla, and they did on the different sites on the body, they did many different sequences, and they end up with 45 minutes. And when you have 45 minutes of MR, and then once again 20 to 30 minutes of PET, you have almost 1 hour or more of PET-MR acquisition. So we are in the old times of PET when PET was without PET-CT, and this is nowadays not really reasonable. So there's really a need for speed. And what when looking at this time, CT scan, it takes around about 30 seconds, and with contrast enhanced CT, it takes approximately over 2 minutes. MR, as shown previously, can reach up to 45 minutes. When looking at trunk now with the new scanners, you can really get down from 10 to 20 minutes or 25 to 50 minutes when scanning the whole body. You can get down to lower times, but overall for PET-CT scanning right now on the new machines, you can do it in 10 to 15 minutes. If you do a whole body protocol, it still takes almost 1 hour. And the problem of PET-MR, it takes at least a quarter of an hour up to 1.5 hours. So therefore there's some need for speed. Other question is, how do we get from the MR images to a reliable attenuation map? Let's say it from MR sequences to pseudo-CT derived from MR, how to calculate the attenuation map. There are different methods which have been used and published in the early years. I don't want to go too much into details there. One thing is that you use, like for example in SPM, you use an atlas and you compare each patient's data to one of the models which was derived from an atlas, and perform the attenuation correction. The other one is tissue classification, which was done for the first time in Munich, and that means that they are using 2 different MR series, and I think this will be the way in the future. We just have to determine the MR series which are used. Different T1, T2 series in order to determine lung, soft or lung or nothing air, soft tissue and bone, in order to have a reliable attenuation map to correlate this, to correct then the CT, the PET data for attenuation. And here is one of these cases. On the upper row is the PET-CT from this patient, then the PET-MR. Here we can see the derived MR attenuation map, and the image quality is quite comparable. So this was an approach which was quite good working. Other thing, just here an example, also they did pulmonary nodules. If the nodule is big enough, it can be recognized and deliver nice images. If it's small, we still have many problems in lung. Other thing which was also published by the Munich group, by the Tübingen group, sorry, was attenuation correction with pattern recognition. So they used using a complex mathematical algorithm, what they did was looking at the brain, at the MR sequence, and they classified gray matter, white matter, and even bony structures and air by recognition of how the behavior to MR, constructed the pseudo-CT and compared it to the real CT, and when looking at these images, it's quite comparable, quality is quite good, and also when looking at these brain scans quantitatively at the first SUV measurements were not significantly different between them. What was our approach now together with Philips is that we went into these different MR series, and there we went rather for Dixon sequences, a 3D Dixon T1, in-phase, out-phase fat set, which provides now excellent image quality in comparison to the conventional algorithm with excellent resolution of 0.8 millimeters. And the acquisition time when looking at 8 stacks, which covers really the whole body from the brain to mid-thigh, we are arriving at a scanning time from 2.5 minutes, which is really reasonable and is from a scanning time comparable to the old system, but image quality is rather better at the time. And as I said, this was the beginning, and now what we are working is in-phase imaging, fat imaging, water imaging. From these we are creating the attenuation map, and there we are getting to the corrected PET images. Finally, in the brain, there were also some people working in real quantification, because if you're looking at subtle changes in the brain, visual analysis only is very often not finding the diagnosis, so you have to do quantification. And these groups worked also with compared transmission-guided attenuation map with MR-derived attenuation maps using T1-weighted MR, extracted the brain tissue, and then calculated there from the attenuation map. And what they were finding was, in terms of image quality, it was comparable when looking at transmission and MR-guided. But what is interesting, however, when looking at, once again, from radiation or from a normal transmission and MR transmission, when then they subtracted the two brain scans one from another, there were significant differences in several regions of the cortex, especially here in the parietal and occipital cortex. There were rather lower activity in the PET-derived acquisition, and in the frontal part there were rather higher activities measured. One other thing is how to image bone, which is still very difficult in MR-guided attenuation correction, but also there are now new UTE sequences which are working on that. And when looking at these images, that gives really nice images of trabecular bone, of cortical bone, and there I think we are also on a good way. So in conclusion, there was a rapid and parallel development of clinical, of first preclinical and then clinical MR, PET-MR. We know that there are different approaches to PET-MR by the different manufacturers, which I mentioned already. Some issues are still challenging. One is state-of-the-art PET technology combined with MR. So how can we perform also in integrated systems one day full-time time-of-flight PET-MR? There's clearly a need for speed in MR, because if PET-MR will survive, it's the MR part which is very important. In the PET we are in the right direction, but MR needs to get faster. Finally, the clinical applications. On one hand, we have a big profit by a decrease of the radiation exposure. Every indication where excellent soft tissue contrast is needed will be interesting for PET-MR imaging, and especially there where MR is absolutely needed, CT is facultative, there PET-MR might replace PET-CT, but at this time, these are just a few indications. And on the other hand, a question which is not resolved, I think, everywhere where PETMR is used, how are the costs developing, and how can PETMR can be reimbursed in the future. And with that, I would like to acknowledge the different people who helped me to put together this presentation. From our department in Geneva, Professor Ratib, the head of department, Habib Saidi, our PETMR physician, Professor Becker from the radiology, from Siemens Healthcare, Thomas Brenneman, who provided the Siemens PETMR images, Professor von Schultes from Zurich, who provided the GE images. And with that, I'd like to thank you for your attention.